Swayam Prabha. Digital India. Educated India.
Let us move on to our next topic, stability. See, in this short series of 2 lectures, we will confine our attention to find out the stability of columns, and we will do the mathematical analysis. Wherever you come across compressive loads, whether it is in bending or torsion or even in shear, you will have to keep at the back of your mind, if the compressive stresses exceed a limit and your optimized structure has minimal thickness in those areas, it can lead to buckling. But mathematically, for this purpose of this course, we will confine our attention to columns. And normally, one of the fallout of this discussion is students tend to think only columns buckle. I want to caution you, we do a mathematical analysis for columns. We do not have the mathematical background to analyze for other situations. Wherever you have compressive load, you have the problem of instability. And you have studied in an elementary manner, even in your physics courses and also in your rigid body mechanics. There, we investigated what is the potential energy. And potential energy, we had used the symbol capital V. See, mind you, when we discuss advanced mechanics, there is paucity of symbols. You can't have one symbol reserved for the entire course. In this course, we have used capital V for shear force. And while we developed rigid body mechanics, we had used capital V for potential energy. So, understand the relevance of the symbol with respect to the concept that we are discussing. Okay. So, when you have a stable equilibrium, if I disturb it, you have a restoring force, it brings it back to the position. It is a simulation which is very closely representing it. All these motions, one has to do it with free hand. There is no geometric curve I can fit in. Okay. At least the PowerPoint people should learn from this lecture that they should have such facility incorporated in the future versions. It is all free drawn, so it is difficult to do beyond a point. And I have a situation, when I have a situation like this, when I disturb, it does not come back to its original position. You have investigated what is the sign of the d squared v by dx squared, then you say it is unstable equilibrium. And you also have a situation when all these differentials are 0, dv by dx, d squared v by dx squared, dq v by dx cube and dn v by dxn, when all of these go to 0, when you disturb, it goes to another equilibrium position. See, it is only an illustration. The other equilibrium position can be of different shape. That is what we are going to look at in stability of columns. So, you have an idea, it does not become like what you have in unstable equilibrium, it occupies another equilibrium position. How the transition is? Here the transition is smooth. The illustration what I have given is the transition is smooth, which is not smooth in stability of columns. Okay. And once you say column failures, one of the things that you can think of is the material failure. You have a compressive material failure when you have a column which has a big cross section. When you see the next set of slides, you will see that those columns are thinner compared to this. And when I have a short column, you can have a compressive material failure. So, it usually happens for columns that are very short and thick, it just crumbled, fine. You also have what is known as a buckling failure. It is called lateral bending or bowing of the column shape. and which is very beautifully illustrated in this animation, in this experiment. And you should also recognize, I am using discrete weights. If I have to do instability analysis, I should have a provision to increase the load gradually. I don't have that provision in the experiment. So, in that sense, this experiment is little crude. Nevertheless, it illustrates a very important basic aspect of buckling beautifully. And what you have here is, you have the boundary conditions. Okay, I have this as pinned end and this also pinned end, and you can identify, because you have already looked at bending deflection, by looking at the deflected picture near the load application point, near the support, you can always figure out what is the boundary condition that is being simulated. Can you tell me what is the boundary condition simulated here? Close to fixed end. Fine. And this is also fixed end and this is also fixed end. So, when you have columns that are long and slender, you have the problem of buckling. And one of the aspect is, when we have a structure which is supported by columns, you do not want buckling to happen. Okay. So, what people have done is, they have done the mathematical analysis and also based on experience, they find there is a load which is labeled as a critical load, beyond which, if there is any lateral disturbance, even a small disturbance, it will go into buckled shape. The load by itself does not introduce buckling if there is a disturbance. Okay. Now, the question is, from where the disturbance comes? That also had to be looked at. See, I have just now said that you have what is known as neutral equilibrium. When I disturb, it goes to another equilibrium condition. I am not sure how many of you looked at this experiment closely. Please watch the experiment closely. You have the idea of this neutral equilibrium beautifully illustrated in this. See, in the first case, I have applied a load which is much beyond the basic critical load, so it has assumed this shape. The second one, you look at it. Can you see that it has started deflecting? See, what you will have to look at is, when you increase the load, it cannot remain straight. You want the column to remain straight. If it does not remain straight, then it is a problem. If you look at this, this satisfies the equilibrium. And suppose I increase the load further, it goes to another equilibrium position. You get the idea? It goes from one equilibrium position to another equilibrium position. And look at the fixed end. You could see that beautifully. I have this load, I have the deflection. So, the system is in equilibrium, not with the column being straight, but in a deflected shape. Suppose I increase the load further, you could see that it has taken another shape, and I increase it further, it takes another shape. So, it beautifully illustrates the buckling phenomena. What you see is actually neutral equilibrium. It cannot remain straight. The moment it cannot remain straight, our functionality of the column is lost, and we do not want to reach that in our structures. That is the idea behind it. And you will also see, I have a concrete beam. So, you could see visibly the cross sectional dimensions are much smaller, and see it has buckled. Fine, it has beautifully buckled. Then in practice, you could have a combination of both compressive and buckling failures. I do not have an image which illustrates that. This happens when length and width of a column is in between a short thick and long slender column. We have already looked at, in this course we are going to work on slender members. Fine. All our discussions are confined to slender members. At times we may borrow that and use it in even in a spur gear teeth, they analyze the gear teeth as a beam, cantilever beam. You may make some corrections of it. Engineers try to solve a given complex problem as best as possible. You should appreciate from that perspective. Okay. And I want you to look at this animation very, very carefully. See, this illustrates what is instability beautifully. See, when I have the load as blue, it is going on increasing, fine. At some point, without a warning, see, that is what you have to look at. If there is a alert, if there is a warning, see, if you have your gas cylinder at home, if there is a leak, you get a smell. Naturally, the gas has no smell. From safety consideration, the manufacturers and the courts dictate that you should induce that smell so that you detect that there is a leak. Before a catastrophic blast takes place, you have avenues to avert it. Either you go and close the gas cylinder, or at least open your windows, or run out of the place. Any of those options which is possible within the time that you can take. If there is a failure which happens without a warning, nothing can be done. In fact, yesterday, 2 days back, there was a bridge collapse, 100 years old bridge collapse in Gujarat. It failed in seconds. That's mainly because one of the possible reason from stress analysis point of view is, in a suspension bridge, you are not supposed to make any periodic oscillations. It seems that revelers did periodic oscillations that would have created a resonance, that would also added, apart from the weight, apart from poor maintenance, it would have also added from a structural point of view for a failure all of a sudden. So, if you look at here, when the load becomes red, it buckles. We don't want that to happen. Okay, I have taken a column that is circular. Fine. I have shown buckling in one way. Was there any visible external interference to this? I said, when you apply the load, if there is a perturbation from outside, you can have buckling. There is no restoring force to bring it back to original shape, so it buckles. See, in this course, to make our life simple, we have said we have an elastic continuum. Our mathematics, we could develop it so beautifully. When delta x goes to 0, there was material available. But real material, how they are? They all have defects. So, one of the perturbations that can precipitate buckling can come from inherent defects on that column. See, I have a circular cross section. I have already told you how does the mathematics understand the cross section. How does the mathematics understand the cross section? You have the moment of inertia. Fine. Suppose I take any axis when the geometry is circular. What is the moment of inertia on any of these diagonals? The moment of inertia, not polar moment of inertia, I am talking about inertia about an axis. Because it is circular cross section, the moment of inertia is same. So, the probability for buckling to happen can be any direction. It can buckle like this, it can buckle like this, it can buckle like this, it can buckle like this. Please understand that. Some of these concepts do not come out very clearly when you read a book, because the book publisher wants to minimize the pages. So, the author can show only buckling in one direction. If you have seen buckling to the right or left, whichever way you look at it, I see it as left, you see it as right. Okay. You will think always buckling happen in one direction. No, it is dictated by the moment of inertia. Because I have taken a circular cross section, the probability exists in all the 360 degrees. It could be precipitated by inherent defects. It could also be precipitated when I apply the load. I may not apply it exactly along the axis as intended it to be. There could be an eccentricity. So, there is a perturbation introduced in the process itself. Suppose I take a rectangular cross section. Here what happens? You should be able to say, I have the rectangular cross section, which way the probability of buckling can happen. Why it is so? Very good. So, what happens is you have the moment of, it will buckle in the direction where it has the least moment of inertia. Fine. So, I have also modulated the expression in that fashion. So, we will see. So, you have to appreciate what causes the column to be in a state of unstable equilibrium. Introduction of the slightest lateral force will cause. That can be inherent in the material itself. Okay, there could be material defects, or there could be problem because of the loading. And column buckling, the credit goes to Euler, and he was a great mathematician. See, if you look at history, people have not had a very healthy life. It seems Euler lost one of his eyes in 1735, and in those days cataract is also a big issue, and he started losing his second eye. He was almost blind, and the Queen of Russia provided him all the support with all assistants, and the buckling was determined in 1757. He had assistants. He would go and explain what he wants. They will translate his work. He was so prolific. He was patronized by the king in Prussia, later in the Queen of Russia. They provided him all the facilities so that he can peacefully work on scientific development. He published his paper at the age of 20. At the age of 16, he completed his master's, and most of his prolific work he did when he was almost blind. Very sad to hear. So, with able-bodied people should at least read your subject properly. Okay, and 1757 is the time he was almost blind at that time. That's what the history says. Okay, and buckling is one phenomena that is greatly influenced by the support conditions. So, that is very clearly seen. See, the critical load drastically changes from one stage to another stage. So, that is what you have looked at it here. And if you ask a question, is buckling is useful or not useful? The question is very similar to whether friction is useful or not useful. Friction is useful for you to walk. Friction is not needed when you want to have your IC engines. And what you have here is, people have used this deflected shape. It's called snap buckling. If I put a force here, it will go to the other shape. This is used in electrical appliances as a switch. So, buckling also has found, and I do not know, when we were young kids, we used to have a toy which is very, very cheap. You will have a simple plate, you press it, it will go to another buckled shape. In the process, it will create a sound, tick tack, like that. Okay, it will be irritating, but toy industry have utilized buckling for entertainment. Okay, in fact, I wanted to get the toy and show it to you. I couldn't get it. And in this chapter, we also make a conscious decision to investigate stability. Even though the deformations are small, the equilibrium requirements have to be applied in the deformed configuration. This I alerted you even long time back. In this course, because the deformations are small, we will work with undeformed configuration for oral mathematics. We make a departure when we want to investigate stability. So, I have shown the beam which is subjected to a transverse load W, and I have this compressive load applied. I have shown this as deflected. We have also analyzed interrelationship between shear and bending moment, where we have taken a load W. There we would have taken this as straight. Go back to your notes and then see. So, the difference what we make is we consciously make, our goal is to investigate stability. Since I have to investigate stability, I do this and I take a small element out of it. So, we consciously make a decision to analyze it in deformed configuration, and I have the deformed shape taken. You can put the shear force, you can put the bending moment, all that follows the usual convention that we have followed. What is extra here? I have a compressive load. Because I have considered this as a deflected shape, you must read this as small v, which is showing the deflection. Okay. So, these loads P are separated by a distance delta v. That is the only difference between what we have done for finding an interrelationship between shear force and bending moment. We had taken this beam as straight. Here we have considered this as deformed, so that I can investigate and I get an extra term in this. Otherwise, the mathematics is simple. Please write down the mathematics. Write down the mathematics. I am going to write the equilibrium equations. I am going to write the force equilibrium. So, that gives me V plus delta V minus V plus W delta x equal to 0. So, force equilibrium in the y direction. And I can also write the moment equilibrium. I have this as mb plus delta mb minus mb plus v delta x by 2 plus v plus delta v multiplied by delta x by 2 plus p delta v equal to 0. So, the additional term what you have is p delta v, and understand this v is the displacement v. Okay. Taking the limit delta x goes to 0 and discarding infinitesimal, that is a usual approximation we do. And we also know the interrelationship dv by dx equal to minus w, and using all that we have dmb by dx plus v plus p dv by dx equal to 0. That is what I am got from the earlier expression. And you will also have to appreciate this does not take account the shear deformation. Even in our bending deflection, the governing equation, we never worried about shear deformation. We were worried only about the contribution from bending. So, the same limitation applies to this expression also. Neglecting the shear deformation, the governing differential equation is obtained. And we know from our earlier knowledge that bending moment is related to the curvature. EI d squared v by dx squared equal to mb, the very famous relation we use for deflection. So, this gives me d squared by dx squared EI d squared v by dx squared, and bracket is closed, plus d by dx multiplied by p dv by dx equal to w. And we have put this in a generic fashion, and this is known as bending rigidity. Suppose I consider a cross section which is of constant cross section and the material is same material, then I can take EI also out. Okay. I can take this out and get the final expression as EI d power 4 v divided by dx power 4 plus p d squared v by dx squared equal to w. So, we have got the governing equation for buckling of columns. When you get an expression and you do a systematic analysis, you all feel that you have got the right expression, and mathematics you have done. Let me ask a question, is it an exact expression or an approximate expression? What way it is an approximate expression? Very good, very good. What they are saying is, see, moment curvature relation, we have linearized it. Fine. We have not taken that as non-linear. In fact, it is very surprising when Lagrange and Euler analyzed, they had taken non-linear expression and then did all the derivation. Fine. They have also indicated that. But here we have used only a linearized moment curvature relation. So, in that sense, it is an approximate expression. Where does this hit in our solution? That also we will see. So, it is a general equation for a homogeneous and prismatic section. That means I have one material and then the cross section does not change. And general solution for this is in this form, V equal to the deflection V equal to C1 plus C2x plus C3 sin lambda x plus C4 cos lambda x. And you have multiple boundary conditions. So, when you supply the boundary condition, you are in a position to evaluate the constant C1, C2, C3 and C4, and you are in a position to solve this as an eigenvalue, eigenvector problem. Okay. And we also have simplified lambda, and lambda is nothing but square root of P by EI. So, what we will have to do is, we will have to go and analyze the fixed free, that is a cantilever beam, hinged. Likewise, we can analyze and we can evaluate the critical load. I have a fixed free column. So, the column is deflected under the action of the load P, and this is the length L, and you measure x from this, okay, and you take a deflection as V, and you know the boundary conditions. See, I have 4 constants, I need to have 4 boundary conditions minimum for me to solve. Here you can write the boundary conditions very easily based on the deflection V. What happens to V here? V is 0 here, and then your slope is also 0. So, you have at x equal to 0, dV by dx equal to 0, and your deflection is also 0. So, these go to the deformation picture. We also have boundary conditions based on the equilibrium requirements, okay, that you can write in the NB. Can I have a shear force there? At x equal to L, can I have bending moment there? Bending moment is 0, and your shear force is also 0. So, please understand, you know, when you write, make it a small v, make it as big V. In while writing it in computer, I can do this easily. You must make the distinction, and now you apply the boundary condition and solve for it. I have the boundary conditions, and I have you know, MB equal to 0, that tells me EA d squared V by dx squared equal to 0. I should construct that expression. Similarly, I should construct V equal to d by dx EA d squared V by dx squared plus P dV by dx equal to 0. These two are straightforward. So, I can write the expressions by substituting those values. This is the governing solution. Okay. So, when I substitute dV by dx equal to 0, I get 0 plus C2 plus C3 square root of P by EI plus 0 equal to 0. Then I have V equal to 0. So, I have C1 plus 0 plus 0 plus C4 equal to 0. Then I have MB is 0. So, when I do this, I get this as 0 plus 0 minus C3 P by EI sin square root of P by EI multiplied by L minus C4 P by EI cos square root of P by EI L is outside, okay, it is not inside the square root, equal to 0. So, the fourth condition is shear force is 0, that gives me 0 plus C2P plus 0 plus 0, and this I can put it in a matrix form in a convenient fashion, and you have this equal to 0 0 0. So, this is nothing but an eigenvalue and eigenvector type of problem, and for non-trivial solution this determinant should go to 0, because when the determinant is not 0, the trivial solution is C1, C2, C3, C4 or 0, that is a straight column. Okay. We want a non-trivial solution. So, the determinant should go to 0, and we can evaluate this determinant in stages. I think it is shown. Okay. So, you can expanding the above 3 by 3 determinant. I get this as 0 plus 0 minus p multiplied by p by ei whole power 3 by 2 cos square root of p by ei multiplied by L equal to 0. So, this is the final expression. See, P is the applied load and EI is the bending rigidity. So, P multiplied by P by EI whole power 3 by 2 cannot be 0, because it is a non-zero quantity. So, this tells us that cos square root of P by EI L should go to 0. So, that helps us to construct the solution. Fine. So, you have this, and this is again a multi-valued problem. Okay. Any inverse you will have a multiple values. So, this says square root of P by EI multiplied by L can take the value n pi by 2, n goes from 1, 3, 5 and so on. And you have Pn is given as n squared pi squared EI by 4L squared. And in this what we have done is we have taken the solution for a hinged connection as P star. Compared to P star, all the values for fixed free, fixed hinged, fixed values are indicated. And you also have a rectangular cross section, and your minimum moment of inertia is Iyy. So, explicitly in the expression it is desirable to put I minimum. If I have a circular cross section, I minimum is same as I at any one of the diagonals. But if you take a non-circular cross section, you will have to understand that buckling or the critical load you should look at for the least value. If you take another I, you will get another value, but that may be higher than the least value. You do not want the column to deflect, you do not want the column to buckle in a given application. So, I minimum is a better representation, only least values of importance. So, we will have n equal to 1. That gives me critical load as P critical as pi squared EI by L 4L squared. See, this is for the case of fixed free column. And equation of the reflection curve, when you go back and substitute these values, I get an expression V equal to C1 1 minus cos lambda x, and we know what is lambda. Lambda is square root of P by E. How many of you are convinced with this solution? There is one catch still there. We have used 4 boundary conditions. Fine. Have you been able to find out what is the value of C1? C1 is still indeterminate. What has caused this? See, when I apply the boundary condition, I should get one unique solution or not? See, we have done the linearization of the moment curvature relation. If you do not make that as a linearized solution, if you take that as nonlinear, then you will also be in a position to find out what is C1. But nevertheless, whatever the solution that we have got, good enough for investigating instability. Fine. But you should understand that C1 we have not been able to catch. Okay. See, what you will have to appreciate is experiment is truth. Moment the column has buckled, it is large deformation. We have said our hypothesis is small deformation and we will investigate. Even though it is small deformation, because we want to investigate stability, we go for a deformed configuration to write the governing equation. Until it has buckled, our analysis is all right. Once it has buckled, you have to go for improved mathematics to analyze post-buckling behavior. Suppose I apply a load higher than the P critical, what happens? You cannot do the analysis, but experiments can reveal it. Experiment does not get limited by your poor ability to solve your differential equation. Fine. That is what we had seen in the experiment. We were able to see, we have applied load beyond the critical load, we saw deflected shapes, they are all neutral equilibrium positions. So, do not mix up the experimental result with your analytical analysis. Analytical analysis stops the moment you find the critical load. Beyond critical load, experiments gives you more information for you to ruminate over it. Okay. See, there is also another approach which is usually adopted by civil engineers. They use a second order differential equation. It is discussed for a fixed free column. You have enough background to do that, and this is a statically determinate problem. Okay. Whereas, if you have hinged, even hinged is statically indeterminate. Hinged roller support is statically indeterminate. So, all the other problems are statically indeterminate. While we developed deflection equations, we also developed d power 4 v by dx power 4. We have developed that. We said that equation is useful even for statically indeterminate problems. So, that is why you find that equation is used for developing the critical load, because except the fixed free, all other situations are statically indeterminate. But there is also school of thought that people directly use the second order differential equation approach. So, you have to write the equation when you have this deflected, because of the deflection, this compressive load causes a bending moment P delta. So, if you take an arbitrary section at a distance x, which is measured from the fixed end, you have this as V and this as bending moment M, and m naught is P delta, that is obtained from this. So, if you write for this free body diagram, m minus m naught plus Pv equal to 0. So, this reduces to m equal to plus P delta minus Pv, and then you have d squared v by dx squared equal to m by Ea, which we have learnt in deflection. So, d squared v by dx squared equal to plus P delta minus Pv divided by Ea. So, I can get d squared v by dx squared plus Pv divided by Ea equal to P delta by Ea, and lambda squared equal to P by Ea, which we have already used. You can also rewrite this as d squared v by dx squared plus lambda squared v equal to lambda squared delta. It is a non-homogeneous second order differential equation. Solution to the above equation is of the form a sin lambda x plus b cos lambda x plus delta, and you have the boundary conditions. At x equal to 0, b is 0 and slope is 0. At x equal to L, v is delta. So, applying the boundary conditions in the above deflection equation, we get v0 equal to 0. Because this is straightforward mathematics, there is no difficulty, you have enough background, you can in fact do it much faster than what I am showing. B plus delta equal to 0. So, this reduces to b equal to minus delta and v prime 0 equal to 0. So, this gives me a lambda equal to 0. So, this gives me A equal to 0. So, when I substitute all of this, VL equal to delta, I get delta minus delta cos lambda L equal to delta. So, this gives me again cos square root of P by E L equal to 0, identical same solution like what we have got, and you get the critical load as n squared pi squared EI by 4L squared. Considering the first and minimum satisfying value of n equal to 1, I get the critical load as pi squared EI by 4L squared. Equation of the deflection curve. So, V equal to delta into 1 minus cos lambda x. So, this is another form of analysis. We can do the similar analysis for a pinned column. What is the difference? The difference is only the boundary conditions. Okay. You have the governing equation, you have the basic solution, and you have the expressions. So, it is just substitution of the boundary condition and get this. Okay. V equal to C1 plus C2x plus C3 sin lambda x, C4 cos lambda x, and you have the boundary condition at x equal to 0, V equal to 0, and MB equal to EA d squared V by dx squared equal to 0. At x equal to L, V equal to 0, and you have MB equal to EA d squared V by dx squared equal to 0. So, once you substitute this, I get this set of equations. Okay, it is very easy for you to do that. Please work it out in your rooms. That is also a practice for you. And for non-trivial solution, I want the determinant to go to 0, and that will give me the basic expression for me to find out and investigate what are the eigenvalues and eigenvectors. For non-trivial solution, this determinant should go to 0. Okay, and I have this. This gives me finally, I have an expression like this, and this gives me sine root of P by L goes to 0. And once you investigate this, it will also be all inverse functions are multivalued. So, I have square root of P by EI multiplied by L equal to n pi. So, this goes to Pn equal to n squared pi squared EI by L squared, and this is a basic expression which is used for comparing what happens in fixed free, that is like a cantilever beam. So, if you look at this, shows what is the critical load for a cantilever. It is 1/4 of the critical load in pin-pinned condition. When I have a fixed and pinned, it is twice the load. If I have the fixed, it is 4 times the load of the pinned condition. So, that is how the graph is plotted, and this simulation is also good. It shows you the buckled shape alternately. To remove the mental block that buckling happens only towards your left or right, it is precipitated by inherent defects or even external disturbance. If there is a breeze going from one side to another side, that can also precipitate buckling. If the wind direction changes, so the buckling is precipitated by the disturbance and also dictated by the I minimum. You should have both in your mind. And when I have n is greater than 1, when n is 1, you have this simple shape, first mode of buckling. I have this as pi squared E by L squared, and when I have n equal to 2, I get the second mode, and P2 is 4 pi squared E by L squared, and when I have this n equal to 3, I have the third mode. See, in vibration problem, all of these modes are important. In the case of buckling, higher modes are difficult to get unless you do prompting of the notes experimentally. Okay, and my TAs have done a very good experiment. I will show you that also. And you have the P critical is pi squared E A by L squared. I would urge you to write this as pi squared E I minimum by L squared. Okay, that is what I have shown it in my animations here. Now, let me look at this deflection curve as C3 sin lambda x. So, you are not in a position to find out what is the magnitude of C3, that is because you have linearized the moment curvature relation, and you have multiple equilibrium positions possible, and let us see the experiment. Okay. You have to put your restraint at the node. For the given load, these higher order positions are not realized in practice unless you prompt the structure to have that. So, this is a very nice experiment my TAs have done, and it shows you can have this shape. You understand? You can have this shape, and so there were mathematical analysis not for fun. What you see, it's too difficult to realize that you can have the column bent like this. And long time back, we had also seen torsional mode of vibration of the tachyon. You will not realize concrete bridge can motions. Fine. It is possible provided the experiments are. So, in this class, we have looked at stability. I said the stability is an issue where from a mathematical analysis point of view, we will confine our discussion to column buckling, and because investigating stability, we have to write the governing equation in a deformed configuration. We find out the critical load. The moment I get and the column has buckled, I can see deformation very clear. You do not have the to get the deflection. Requires higher for you to do it. Thank you.